So in this video, we're just going to use the formula for matrix inverses to calculate a matrix inverse. So here's a matrix. We actually saw this matrix in video 2. And in video 2, we calculated the cofactor matrix for this matrix A, and we calculated the adjoint matrix for matrix A. And all we're going to do is use the formula that A inverse equals 1 divided by the determinant times the adjoint matrix. So in video 2, the cofactor matrix for A, we calculated it to be the following. I wrote it down. It was 3, negative 17, 4. It was negative 1, negative 7, and 5. And negative 3, negative 2, and negative 4. Which means that the adjoint of A is just going to be the transpose of this matrix. So the first row became the first column. The second row became the second column, and the third row became the third column. So we have the adjoint matrix, which we already calculated in video 2 for this particular homework series. So all we need to do is calculate the determinant and make sure the determinant isn't equal to 0. But the determinant calculation for A should be simple because right here we have the cofactor matrix. And remember, determinants are defined in terms of cofactor expansions with respect to a specified row or column of your choice. So for example, if I choose to find the determinant of my matrix A using row 1, then I'm going to look over here and say, hey, I have the cofactors that go with each of these elements in row 1. So I can take the row 1 column 1 element times its cofactor, which is 3. And I don't need to worry about the plus minus plus pattern because the cofactors already have calculated into them the plus minus plus pattern. So I would do negative 2 times 3 plus element 4 times cofactor of negative 1 plus element 3 times the cofactor negative 3. And then we would just do the arithmetic. This would be negative 6 minus 4 minus 9 is going to be minus 10 minus 9 is negative 19. So we have a non-zero determinant, which means the inverse exists and we can calculate it. We could just as easily have calculated the inverse using any row or column in A. So for example, row 2 probably would be the best choice because I have 1, 0, 1 for my elements. So for example, I could have gone the element 1, which is in row 2 column 1, I can multiply it by the row 2 column 1 cofactor. So I would be using row 2 here. So 1 times negative 17 plus 0 times the negative 7 plus 1 times the negative 2. And I'm going to wind up with negative 17 minus 2. I'm still going to get the negative 19. The determinant doesn't care which row or column you use to calculate it. And the idea is if I use this formula, I have to calculate the cofactor matrix anyways. I might as well use the cofactor matrix to calculate my determinant. So now I can get my inverse easily. My inverse is going to be 1 over the determinant. So that's going to give me 1 over negative 19, or just negative 1/19, times the adjoint matrix. The adjoint matrix is just sitting right here. Four, 5, negative 4, and there is the inverse. No real need to distribute the negative 1/19 into the matrix. And again, Gauss-Jordan elimination would be an easier method for calculating the inverse. The adjoint matrix and the cofactor matrix, which we needed to construct the adjoint matrix, took a lot of calculation. We had to do, we had to calculate 9 cofactors. So not efficient, but you can get the inverse this way.